This data compares a measurement of the Earth's rotation taken in the year 499 CE with one taken by modern satellites. The modern measurement is 23 hours, 56 minutes, and 4.09 seconds. The ancient calculation, 23 hours, 56 minutes, and 4.1 seconds. That same 5th century astronomer also calculated the length of the Earth's year. He pegged it at 365 days, 6 hours, and 12 minutes, differing from our modern standard by only a few minutes. The mathematician behind these numbers was a man named Aryabhatta. He achieved this level of numerical precision without a single optical telescope, relying entirely on naked eye observation and pure mathematics. Doing this meant overcoming a massive physical hurdle. To a human standing on the ground, the night sky is highly deceptive. This animation tracks a phenomenon called retrograde motion. Because the Earth is moving along with the rest of the solar system, other planets appear to be slowing down, stopping, and actually reversing course against the background stars. To solve that visual paradox, Aryabhatta compiled his masterwork, the Aryabhatta. It is a mathematical engine explicitly built to strip away these visual errors and calculate the actual positions and periods of the planets. Before Aryabhatta could accurately chart the orbits of distant planets, he first had to isolate the motion of his own observatory. He had to map the Earth. At the time, standard observations suggested the sky spun around us. Aryabhatta deduced that the daily rising and setting of the stars is actually an illusion caused by the Earth rotating on its own axis. To explain this perspective, he wrote, "Just as a person in a moving boat sees the stationary objects on the bank as moving backward, just so does an observer see the fixed stars as moving westward." Once he proved the observer was spinning, he needed a second variable, a flawlessly rigid timeline. Human calendars break down over centuries as fractional errors shift dates and ruin long-term astronomical predictions. To fix this, Aryabhatta used the Ahargana system, literally meaning a heap of days. Instead of dealing with months and varying years, he simply kept a running tally of total days elapsed since the beginning of a specific ancient epoch, a spinning observer, and a strictly linear day count. By stabilizing those two variables, Aryabhatta created a clean mathematical framework ready to handle the heavy lifting of planetary motion. Next came the planets themselves. For the sake of computational convenience, Aryabhatta mapped everything using a geocentric or Earth-centered coordinate system. It was easier to calculate positions from the perspective of the observer. But observing from Earth creates those visual anomalies we saw earlier. Perfect, simple circles fail to predict where a planet will actually appear in the sky. To fix this, he introduced mathematical corrections. This schematic shows his first correction, the mandaka, or slow epicycle. Instead of orbiting Earth in one simple ring, the planet traces a smaller circle, the epicycle, while the center of that small circle travels along the main orbit. This accounted for variations in orbital speeds. Then, for the inner planets, he added a second correction. Watch as this faster-moving loop, called the Siraka, is applied over the first. The planet's calculated path becomes a complex compounding geometric spiral. When we track this model for Mercury and Venus, the center of this fast epicycle aligns exactly with the mean position of the Sun. Aryabhatta never explicitly placed the Sun at the center of the universe. But by tying his epicycles to the Sun's position, he mathematically accounted for heliocentric reality, keeping planetary predictions consistent with observations year after year. The formulas inside the Aryabhatta became the source code for Indian mathematical astronomy for the next 1,000 years. Crucially, his system prioritized computational accuracy over doctrine. When future astronomers found tiny discrepancies in the sky, they were expected to sit down, revise the algorithms, and bring the math back into agreement with physical reality. That tradition of iteration leads us forward a millennium to the 15th century Kerala school of mathematics and an astronomer named Nilakanta Somayaji. Nilakanta followed Aryabhatta's mathematical thread to its logical conclusion. This map illustrates Nilakanta's breakthrough, a geo-heliocentric system. The 5 visible planets orbit the Sun, and that entire planetary system then orbits the Earth. Decades later, the Danish astronomer Tycho Brahe would propose this exact same structural model in Europe. By recognizing the deep flaws in human perspective, Aryabhatta handed future generations the tools to correct their own vision. He built the mathematics necessary to strip away the illusion and finally map the sky as it really moves.